Hello students! Matrix methods for solving systems of equations. Now a matrix is simply a rectangular array of objects. Systems of linear equations can be solved by converting the system to an augmented matrix, which can be manipulated to reveal the solution. We have three systems here. First system is two equations with two unknowns, x and y. And what you really want to do is make sure your equations are lined up so that the ordering of the variables is consistent from equation to equation. In other words, the x's are over the x's, the y's over the y's, then you have the equal sign, and then you have numbers on the other side. Then you simply have to write the coefficients of x and y, 3 and 1, and then the other side of the equal sign, you have a 4. So this first equation just translates into 3, 1, 4. This second equation will translate into 5, 2, negative 1. And then you put the matrix in a set of square brackets like this. So this matrix has 2 rows and 3 columns. Sometimes what's done here to represent the location of this equal sign is a vertical line is placed in the augmented matrix. So the first column represents the x coefficients, and the second column represents the y coefficients. When we have x, y, z, we typically go in that order. So this first equation, begin by writing the coefficients of x, y, and z, and then the constant on the other side of the equal sign. Now, the second equation, things are a little bit scrambled. So you want to make sure you unscramble them before you put the numbers into your matrix. So you still want to put the coefficient of x first, and the coefficient of x is negative 1. Then you want to put the coefficient of y, and the coefficient of y is 3. Then the coefficient of z, which is also negative 1. And then this minus 4 should be added to the other side of the equal sign, and it would be a positive 4. And this last equation, the coefficient of x is 5. The coefficient of y, well, currently y is on the wrong side of the equation. Here you want to subtract y from both sides and add 2 to both sides. When you do this, the coefficient of y will be negative 1, the coefficient of z is 3, and then the constant on the other side of the equal sign will be a 2. And the columns represent the coefficients of x, the coefficients of y, and the coefficients of z. And then finally we have two equations. Look at the total number of unknowns. We have w, x, y, and z. We have 4 unknowns. And you can decide what order you want to put these columns in. You just want to be consistent. If you decide that w should be first because it comes before x alphabetically, then some people do that. So let's do a w column, then an x column, then a y column, then a z column. And there's only 2 equations here, so we're only going to have 2 rows. So in the first equation, the coefficient of w is 2. Coefficient of x is 1. Coefficient of y is negative 1. And coefficient of z, well, there is no z, so you can just put a 0. And then on the other side of the equal sign is a 9. Now the second equation, which will be our second row, the coefficient of w is 3. The coefficient of x, there isn't an x, so it's 0. The coefficient of y, there is no y, so it's also 0. And then the coefficient of z is negative 1. And then this 8 here should be subtracted to the other side first. So you would have negative 8 on the other side of the equal sign. Okay, so this is how you convert systems of equations into augmented matrices. Now, a matrix is said to be in reduced row echelon form, which is RRE form, if it meets the following conditions. First condition, if there is a non-zero entry in a row, then the first one you come across from left to right is called the leading entry. And to be in reduced row echelon form, the leading entry has to be a 1. The second condition is that leading ones appear further to the right from row to row. So as you go down the rows, your leading ones, you find them in columns further and further to the right. Number 3, any rows of all zeros are at the bottom of the matrix. And number 4 is all other entries in a column with a leading one are 0. Now, determine which matrices below are in RRE form, reduced row echelon form. For those matrices that are not in RRE form, explain why. Okay, so we're going to do one matrix at a time and just analyze the 4 conditions. Condition 1, the first non-zero entry of each row is 1. So let's zoom in. I'm going to highlight the leading entry. So there's the leading entry, and it's a 1 in that row. The next row, the leading entry is way over here in the third column. It's also a 1. But in the third row, the leading entry is a 9. So right away, we can say that this is not reduced row echelon form. R3 will stand for row 3, violates condition 1. Okay, so there's no sense in doing the other conditions. Let's look at the next matrix here. I'm going to highlight the leading entries, the first non-zero entry in each row as I look left to right. So they're all 1s. So the first condition is met. Now we look to the second condition. Leading ones appear further to the right from row to row. So when we look in the first row, the leading 1 is in the first column. Look at the second row, the leading 1 is further to the right, it's in the third column. When I make this jump from second to third row, we see that the leading 1 moved further to the left. So these leading ones violate condition 2. So we're going to say that this is not in reduced row echelon form. We're going to say rows 2 and 3 violate condition 2. Okay, now let's look at the next one. I'm going to highlight all the leading ones. There's a leading 1 there, and the second row has no leading 1 because it has no leading entry. There are no non-zero entries in the second row. And the third row has a leading entry that's also a 1. So condition 1 is met. There's only 2 leading entries, and they're both 1s. Also, condition 2 is met because the leading 1s are further to the right from row to row. Condition 3 states that any rows of zeros, if there are any, are at the bottom. Well, this row right here is a row of zeros, but it's not at the bottom, it's in the middle. So condition 3 fails. So this is not reduced row echelon form. Or I suppose you could say row 2 violates condition 3. Okay, now let's look at this fourth one. Here's a leading entry and here's a leading entry. And those are the only leading entries and they're both 1. So condition 1 is met. Condition 2 is also met because the leading entries are further to the right as we go down the matrix. Condition 3 is also met because there is a row of zeros and it's at the bottom of the matrix. Now condition 4, what condition 4 is stating is that all other entries in a column with a leading 1 are 0. So when you look at your columns that have leading 1s, and there's only 2 columns, this column and this column, the third column here does not have a leading 1, so condition 4 does not apply to this. But when you look at this column here, we have the leading 1, and it has to be that all other entries in that column have to be 0, and that's true for column 1. Now column 2 also has a leading 1, it's right there. And condition 4 states that all other entries in this column have to be 0. So this 4 is not 0, which is violating condition 4. So we're going to say not reduce row echelon form because column 2 violates condition 4. And now for the last one. You can probably guess what's going to happen here. 2 leading entries, they're both 1s. They do appear further to the right as we go down the matrix. We do have a row of zeros, it's at the bottom of the matrix. And the only 2 columns that have leading 1s have zeros everywhere else. Condition 4 only applies to the columns where there are leading 1s. And so this one is RRE form. Okay, next slide. A row operation on a matrix is any of the following actions. Number 1, multiply all entries in a row by a non-zero constant. Number 2, interchange any 2 rows. And number 3, replace a row by adding a multiple of another row to it. It's going to turn out that these row operations do not affect the solutions of a corresponding system. That's simply because if a row represents an equation, like this row right here might represent negative 5x minus 4y is equal to 12. And if you take an equation, you're allowed to multiply both sides of it by any non-zero number you want. That would effectively just multiply this entire row by some non-zero number. And that will not change your solutions, so you can do that. Interchanging 2 rows is simply like interchanging 2 equations in your system, which doesn't change the set of equations in the system, which therefore doesn't change your solutions. And replacing a row by adding a multiple of another row to it is like the elimination principle that we did with systems, where let's say you double equation 1 and add it to equation 2 so that you can cancel some variables. So that doesn't change the solutions of a system, therefore you can replace a row by adding a multiple of another row to it. So these 3 row operations are the 3 things you're allowed to do to a matrix to manipulate it, but without affecting the solutions. Now we're going to alter the matrix below by performing each row operation at least once in succession, and we're going to notate our work. Notating our work is super important, so you can go back and someone can see what it is you're doing to a matrix to change it, because it's not always obvious unless you notate it. Let's do the first row operation, multiplying all entries in a row by a non-zero constant. One thing I noticed about this matrix right away is that there is a fraction involved in row 3. And sometimes it's unpleasant to operate on matrices where there are fractions. And so we're going to make a new matrix. We are going to triple row 3. So here's my notation, triple R sub 3. Now the first 2 rows I'm not changing. And if you triple row 3, triple the 0 stays 0, triple a third is 1, and triple negative 4 is negative 12. Now let's do row operation number 2. Let's interchange rows 1 and 2. And so what I will do in my notation is say row 1, double arrow, row 2. So row 3 is not changing. Let's move that out of the way. Let's move row 1 down to row 2, and what used to be row 2 back up to row 1. And we've accomplished a row interchange. Okay, the next thing we're going to do, add a multiple of one row to another row. For example, if I were to quadruple this row here, and I'm going to quadruple it only in my head, and then add it to another row. And let's say I add it to row 2. They'll say we'll do 4 times row 3 and add it to row 2 to produce a new row 2. All right, so I'm going to put my new matrix. Let me copy this, paste it down here. And our goal is to change row 2. No other row is changing. So I'm going to erase row 2, get rid of that. And let's go ahead and proceed with our row operation. So I'm going to multiply all the entries of row 3 by 4 temporarily, so just in my head, and then add that to this row in order to make a new row 2. So multiply 0 by 4, you get 0, and add that to -5, and you're still going to get -5. But when I multiply this 1 by 4, and then add that to this -4, we're going to get 0, and 0 goes in this spot right here. And then finally, we're going to do 4 times -12, that's -48, and add that to +12. That'll give me -36, and that goes into my new position. Okay, now the third row operation says replace a row, so we replaced row 2 by adding a multiple of another row to it. So we added a multiple of row 3 to row 2 in order to change row 2. And when we say a multiple of another row, that multiple could also just be 1. So in other words, you could just add 2 rows together to replace a row. So let me just do this row operation one more time just to illustrate that. For example, what if I do 1 times row 1 and then add that to row 2 in order to replace row 2? The way I'm doing this notation is the row that's being targeted for change is the one I write second, and I could do any multiple of another row right here, including 1 times that row. These two right here in this notation should always match. Let me go ahead and copy and paste. Keep in mind that it's row 2 that I'm targeting for change, so no other rows should change from this row operation. We do row 1 plus row 2 to get a new row 2. So 5 plus -5 is 0. And then we do 10 plus 0 is 10. That gives us a 10 right there. And then we do 0 plus -36. That gives me a -36. Let me show you an alternate notation that I like to use. If I triple a row, then one notation is just put a 3 outside that row, and that tells me what I've done to this row. I've tripled it. When I do a row interchange, like interchanging rows 1 and 2, then I just do a double-sided arrow pointing at the 2 relevant rows. Now when I do 4 times row 3 and add it to row 2, what I'll do is I'll put a 4 outside row 3, but then with a single directional arrow pointing at row 2. So this tells me to multiply this row by 4 and then add it to this row to change that row. And when I add row 1 to row 2, I can put a 1 here if I want, and then a single arrow to row 2, or sometimes I don't even bother writing a 1. If I do a single arrow like this, this is my way of saying, hey, take this row, add it to this row in order to change this row. Now moving forward, I'm going to use my orange notations here and not the red notations. Row reduction is the process of putting a matrix into RRE form using row operations. And Gauss-Jordan elimination is the process of row reducing specifically an augmented matrix to determine the solutions of the corresponding system. Do this for the system below. All right, the first thing that we want to do is write this as an augmented matrix. Now make sure everything's all aligned, all the x's are aligned, all the y's are aligned, and all the z's are aligned, and all the constants are on that side. So this will be easy to convert. We just have 2, -1, 1, 7, and then we have 1, 1, -1, 2, and then there's no x in the third equations, so we have 0, but then we have 2, 1, and 4. So here is our augmented matrix, and my objective is to put this into reduced row echelon form. And if we go back to these reduced row echelon form examples, getting this column to be a 1 and then a 0, 0 is our first objective. Once that's done, we're going to shift our focus to get the next column to look like 0, 1, 0 if possible. And then we'll continue and we'll try to make this one look like 0, 0, 1 if possible. And so I'm going to come back to this problem right here and analyze the first column. If there is a 1 already somewhere in that column, then do a row interchange to put it at the top. So I'm going to row interchange rows 2 and 1. So I'm going to highlight that leading 1. I do not want that to change. Now I want these both underneath it to be 0. So 2 is the only thing I need to turn to a 0. And the way to turn this into a 0 is to use row operation 3 and this leading 1. So ask yourself, what do you have to multiply 1 by so that when added to 2, it becomes 0? And the answer to that is -2. So if I multiply row 1 by -2, temporarily multiply it by -2, not permanently, and then add that result to row 2, I can produce a new row 2. So let me go ahead and copy this. Now row 2 is targeted for change, so those are all going to go away. And I do -2 times 1 is -2. Add it to 2 makes a 0. So we get a 0 beneath that leading 1, which is what I want. Now I have to continue this. -2 times 1 is -2, and add it to -1 is -3. So the next thing I get is a -3 right here. Then we do -2 times -1 is +2, and then add that to 1 gives me +3. And then finally, Negative 2 times 2 is negative 4, and then add that to 7 is positive 3. Now take your time doing this. It's very easy to make a mental mistake, and once you get a wrong number in your matrix, you'll be very frustrated at how much time is wasted. Okay, so our first column is considered finished. Now we shift gears. We want this entry to be a 1, and you have a couple ways of doing that. You can multiply this whole row by negative 1/3, and that will make this a 1. And conveniently enough, that's also going to prevent fractions, because all three of these entries are all divisible by 3, which is perfect. If you want to avoid fractions, and I do recommend you try to avoid fractions, let's pretend just for a moment that that was a 5. I would be very hesitant to multiply everything by 1/3 right now in order to get a 1 here, because it's going to make a fraction right here. And if we can avoid fractions, we should strive to do so. And there are lots of creative ways to do this. Well, I can't use that one, because if I do a row interchange, that's going to put a 1 here as well. And I don't want to mess up this first column. So I can't row interchange this 1 into this position. But I could add 2 to negative 3. That would make that negative 1. And all this addition that we do here will not create any fractions. And once that's a minus 1, you can turn it into a positive 1 by multiplying that row by negative 1. So there are a variety of ways to go about creating ones where you want them without necessarily producing a fraction. Now, I'm not saying that you can always avoid fractions in your matrix work, but if you can, you should look for ways to do so. But because every single entry in this row is a multiple of 3, then it just makes good sense to me to just go ahead and multiply row 2 by negative 1/3. And I'm picking negative so that this will go to a positive 1. When I multiply row 2 by negative 1/3, I get a positive 1 here, and a negative 1 and a negative 1 in the other entries. Okay, now the leading entry of the second row is also now a 1. Now I'm going to jump to condition 4 of RRE form. I want this to be 0 and this to be 0, and I'm going to use this leading 1 to do it, because there's a 0 here. When I do the third row operation using this second row, the presence of this 0 will have no effect on these entries. In other words, the first column will stay the same, which is what I want. So I have to ask myself, what do I have to multiply 1 by so that when added to 2, it cancels? And the answer to that is negative 2. So I write a negative 2 next to row 2 and with a single arrow pointing to row 3. And that'll turn this 2 into a 0. And then at the same time, I'm going to turn that 1 into a 0. So once you get a leading 1 in a column, in the same step, you could 0 out all the other entries. To use this 1 to turn this 1 into a 0, I need to multiply row 2 by negative 1 and then add that back up to row 1 to make a new row 1. Okay, so let me copy this matrix. These entries are all going to potentially change. The first column will not change, and I will verify that that happens. So let's do the first row operation indicated by doing negative 2 times row 2 and adding that to row 3 to make a new row 3. You have to technically do that to here as well. But when I do negative 2 times 0 and then add that to 0, I still get 0. So I know that 0 there is not going to change. Negative 2 times 1 is negative 2. Add to 2 makes a 0. So we get a 0 in this position. Negative 2 times negative 1 is 2, and add to this 1 gives me a 3. So we have a 3 in that position. And then negative 2 times negative 1 is 2, and add it to 4 gives me 6. Okay, now let's do this row operation to change row 1. So we do negative 1 times 0 is 0, and add it to 1 stays 1. So as wanted, the whole first column was not changed. Negative 1 times 1 is negative 1, add to 1 becomes 0. Negative 1 times negative 1 is positive 1, add it to negative 1 also makes a 0. Negative 1 times this negative 1 is positive 1, and add it to that 2 makes 3. So we get to this point. And our first two columns, they are considered done. Now I want to shift my focus to, and I have a position here, it's a leading position, it's a leading entry, but it's not a 1. So I want that to be a 1, so I'm going to do a 1/3 of row 3, which is really convenient that this is a 6, because I'm going to avoid fractions entirely in this particular example. Copy this matrix, and let's do 1/3 of that bottom row. So we're going to do 1/3 of 3, which is 1, and 1/3 of 6, which is 2. And now I have another leading entry that's a 1. And you can see that already I have a matrix that satisfies conditions 1, 2, and 3. I don't fully satisfy condition 4 yet. I'm going to focus on this final column. The leading 1 is at the bottom of that column, and the other two entries have to be 0. One of them is already 0, that one, so I don't have to worry about that. But this one I need to make 0. When you're focusing on a column, use the leading 1 to 0 out the other entries. So I'm going to use this 1 to make this a 0. And the row operation needed to do that is simply add row 3 to row 2 to make a new row 2. And that will not change anything over here, which is good because I don't want those to change. We are now making a new row 2, but it should be the case that these ones don't change, so I'm not going to erase them, but we're going to verify that those don't change. Okay, we add row 3 to row 2, so add these zeros, and the result is 0, and that goes right there. Add 0 and 1, the result is 1, and that goes right there. So as confirmed, these here do not change. Now add this 1 to that negative 1, and that certainly makes a 0 right here. And then finally add this 2 to that negative 1, and that creates a positive 1 that goes right here. Okay, this matrix now is in reduced row echelon form. It satisfies all 4 conditions. The leading entries are all 1s. The 1s go further to the right as we go down the matrix. There is no row of all 0s, so condition 3 doesn't apply, and condition 4 is also satisfied. Now what we do is keep in mind what these columns represented. This first column was the x coefficient, then the y coefficient, then the z coefficient, and then we had an equal sign, and then the other side. So if you translate these rows into equations now, look what row 1 translates as. 1x plus 0y plus 0z is equal to 3. In other words, it simply translates into x equals 3. The second row translates into y equals 1. And the final row translates into z is equal to 2. And just like that, we found the solution to this system. And I leave it to you to verify. Check that if you plug in 3, 1, 2 in for all the x's, y's, and z's here, that you get all equations are satisfied simultaneously. This also indicates that this is a unique solution situation. Gauss-Jordan elimination is especially useful in describing solutions for those cases where there are infinitely many solutions. Now, each augmented matrix below is in RRE form. Give the solutions, if any, to each corresponding system of equations. Okay, let's focus on this first one. This is an augmented matrix, which means there's an equal sign right here separating that last column. I'm going to highlight the leading ones. This is not in RRE form technically, because the leading entry in the third row is a 7, it's not a 1. But it doesn't change the fact that we have an inconsistent system here. The reason I know that is, look at what this bottom row is when you translate it back into equations. We have an x, a y, and a z column. Row 3 indicates that 0 is equal to 7. And this is a false statement. And if you recall, whenever a false statement emerges in the process of doing substitution elimination, then you know that you're working with an inconsistent system, which just means that there's no solution. Now, if ever in the process of doing row operations, you wind up with a similar situation, all zeros except for the entry on the other side of the equal sign, and that's non-zero. If that happens, you can stop immediately and say that the system is inconsistent. Now, the other ones are in RRE form. Let's go ahead and look at the second example. Let's put a equal sign right here and highlight the leading ones and all 4 conditions of RRE met. This is the x coefficients, y coefficients, and z coefficients. Now, identify any columns that are missing a leading 1. So the z column is missing a leading 1. So we say that z is free. Then I translate the other 2 rows into equations. So row 1 is going to give x minus 5z is equal to 2. And row 2 is going to give y minus z is equal to 0. Now solve these for x and y. So this one reads x equals 2 plus 5z, and the second one would read y equals z. And we know z is free. This is how we can represent infinitely many answers. We can write it as an ordered triplet. So x is 2 plus 5z, y is z, and z is itself. So z is also just z. And z is any real number. And we have infinitely many solutions represented by this. You can pick z to be anything. Let z be 10. If z was 10, then I'd have 52 here, 10, and 10 here. And that ordered triplet would be a solution to the system. And since you can pick z to be anything you want, it's a free variable, you get infinitely many answers, all governed by this relationship between x, y, and z. The next example, this one's also in RRE form. Let me highlight the leading ones. An x column, a y column, and a z column. This time it's y that's free, because y is missing a leading 1. Also notice these rows of zeros. These are not problematic. If you have a row of all zeros, like we do in both these cases, then if you translate that into an equation, it would say 0 equals 0, which is true. When you get a row of zeros, don't think that that means you have an inconsistent system. It's only when you get all zeros except for the last entry is non-zero. So in this case here, I'm going to just translate the rows back into equations. So row 1 will give us that x plus 2y is equal to 2. And row 2 will give us that z is equal to negative 4. So z has to be negative 4, but x will depend on what you choose for y, and y is free. So I'm going to solve the first equation for x. X equals 2 minus 2y. We know that y is free, and z is equal to negative 4. And so our solution, xyz, will be 2 minus 2y, comma, y, comma, negative 4, where y can be any real number. And this would be our solution. Again, this represents infinitely many answers because y can be any number you want. But once you pick it, that'll dictate what x has to be, but z always has to be negative 4. And let's look at this last one. This time, this one has only one leading one right there. We have 2 rows of zeros are at the bottom. And this time it's y and z both that are missing leading ones in their columns. So we have 2 free variables. And row 1 tells us that x plus 2y plus 3z needs to be 4. We'll solve that for x. X therefore is equal to 4 minus 2y minus 3z. And y is free and z is free. And so when you write your solution, it would look like this. X is 4 minus 2y minus 3z. There's my x position. My y position is whatever it wants, and my z position is whatever it wants. And y can be any real number, and z can be any real number, and independent of each other. So you can choose y to be 7 and z to be whatever you want, 8. But once you pick y and z, you got to plug them in here, and that would dictate what x has to be in order to guarantee that you have a solution. Now, keep in mind that these all represented systems of 3 equations with 3 unknowns x, y, z. So we're talking about whether or not planes in 3-dimensional space are intersecting. Inconsistent means that there's no points common to all 3 planes. When you get one free variable, like in these two, that's an indication that the 3 planes intersect along a line. And when you have 2 free variables, like in the last case, that's an indication that all 3 planes intersect in a plane. In other words, they were all the same plane. Okay, so as you can see, putting an augmented matrix into reduced row echelon form is especially helpful in helping us describe the solutions in these cases where your planes intersect along a line or your planes intersect along a plane. Also helpful in revealing whether you have an inconsistent system. Okay, and that wraps up our discussion.